Welcome to the paper of numerical methods in the subject of information technology under EPG Pathshala. In our previous lecture, we began our journey for numerical integration formulas. We viewed and we realized that in the case of definite integral, there are different situations where we need to resort to numerical integration techniques. Namely, either the antiderivative may not be known to us, or the expression for the antiderivative may not be available in terms of ordinary standard functions, or the function may be available only at the discrete data points and integrand may not be known. Under these situations, we have to use numerical integration formulas to get the result correct to desired accuracy. Also, we saw that the numerical integration formulas are of the form of linear combination of the function values at some points, that is weighted average type sigma wi fxi, and these wi's are called weights, the coefficients in the formula, and the xi's at which the function values are used in the formula are called abscissas. We also reviewed that the formulas are of two types, where in the first case abscissas are fixed and only weights are determined in the formula, and second case where abscissas and weights both are supposed to be unknown. We begin the process for the first type of the cases where our abscissas are known and weights are to be determined. These type of formulas are called Newton-Cotes formulas. In these Newton-Cotes formulas, the function to be integrated is approximated by interpolating polynomial, and the integral of the interpolating polynomial is taken as the value of the integral. So, we had taken the case of n equal to 1, that is when the function is being approximated by a polynomial of degree 1, that means linear function straight line. We derived the rule for it, and this rule we saw is called Trapezoidal Rule. The name Trapezoidal Rule is for simply the reason that graphically it represents the area of the trapezium. We also solved one example, a very simple example, to verify the correctness of the result, and we found that the result contained a good amount of error which is not acceptable. And so, we have to look for a better remedial measures so that the formula can give the result correct to desired accuracy. For it to look for other remedial measures or different other options, let us do the error analysis of the trapezoidal rule. In other words, let us derive theoretically the error formula for the trapezoidal rule. Already you have learned in the interpolation that if fx is approximated by a polynomial of degree n, so fx is given by pnx plus ex, where ex is the error term, and expression for the error term is given by fn plus 1, that is the n plus 1 derivative of f at the point xi divided by n plus 1 factorial into x minus x0, x minus x1 up to x minus xn. That is the product x minus xi, I runs from 0 to n upon n plus 1 factorial multiplied by n plus 1 derivative of f at some point xi. This xi point is not known to us, but what we know about the point xi is that it lies within the interval ab. And therefore, see, if this equation we integrate both the sides of this equation. So, integral a to b fx dx, that is our if, is equal to integral a to b pnx dx, that is our integration formula, and plus integral a to b ex dx. So, error in the integration formula is given by integral a to b ex dx. If we can find, or if we can get the estimate of this integral of the error term, this will give us idea about the error term. So, let us proceed to integrate the error term in the case of n equal to 1, means in the case when fx is being approximated by a linear function, or in other words when our approximating integral formula is the trapezoidal rule. So, here when n is 1, only 2 points x0 and x1 our x0 is a and x1 is b. So, the error term for this case is a to b ex dx is given by a to b f2 xi by 2, because n plus 1 is 2 now, there are n plus 1 points, that is 2 points, x minus a into x minus b dx. In order to evaluate this integral a to b f2 xi by 2 x minus a into x minus b dx, we will take help of mean value theorem of integral calculus. Just let us review what the integral theorem of integral calculus says. If fx is continuous and if g is Riemann integral on the interval ab, and moreover gx is entirely positive on the interval or entirely negative on the interval ab, meaning by if gx does not change its sign on the interval a to b, then there is a point xi, or you may call it c, within the interval a to b, means a is less than equal to xi less than equal to b, such that we can write the integral a to b product, integral of the product fx into gx dx as f xi into integral a to b gx dx. Meaning by when we are integrating the product fx into gx, and if gx does not change the sign, then the f at the some point within the interval that can be taken outside the integral sign, and all we are required to integrate is gx. So, this would be very handy in order to enable us to evaluate this integral. So, our integral is a to b f2 xi by 2 x minus a into x minus b. See here 1 by 2 is constant, comes out, and x minus a into x minus b will take the role of g in the mean value theorem. As x lies within a and b, x minus a is throughout positive, x is greater than or equal to a, and x is always less than or equal to b, so x minus b is throughout negative. And so, x minus a into x minus b is throughout negative on the interval a to b, so it does not change its sign, and that is why we can take out f2 xi outside the integral sign. So, we get f2 at some point c, c lies within a to b, so f2 c by 2 and integral a to b x minus a into x minus b dx. Now, in order to be able to evaluate a to b x minus a into x minus b dx, for our ease of convenience, let us change the variable from x to t. So, x becomes a plus th. Let us substitute x is a plus th and we will change the variable of integration from x to t. So, when limits of the integral will become, when x is a, we get a is a plus th, so t is 0, and when x is b, we get b is a plus th, so the value of t becomes 1. So, limits of integration become lower limit 0, upper limit 1, and inside x minus a is th and b is a plus h. So, x minus b becomes a plus th minus a minus h, that is th minus h, and so it becomes t minus 1 into h. So, our integral becomes f2c by 2 and dx becomes h dt. X is a plus th, so dx is h dt. So, what we get is f2c by 2, h comes outside, inside the integral 0 to 1 th into t minus 1 h dt, and h square being constant independent of h, that also can be taken outside. So, h cube by 2 f2c and integral 0 to 1 t into t minus 1 dt. This expression t into t minus 1 is t square minus t, integrate from 0 to 1. So, t cube by 3 minus t square by 2 from 0 to 1, and that is h cube by 2 into second derivative at c, 1 by 3 minus 1 by 2. So, the result is minus h cube by 12 and second derivative at the point c. Our h is b minus a, so we can say the error e is minus 1 by 12 second derivative at c, b minus a cube, where c is some point in the interval a to b. And so, the error what we get is proportional to h cube, the length of the interval. If second derivative is bounded by constant m, we can say that error is less than or equal to minus 1 by 12 m multiplied by b minus a cube. And so this gives the idea that if you want to reduce the error in the trapezoidal rule, we should be able to work with smaller h. But how to work with smaller h? If you want to integrate a to b, b minus a is fixed. So for it, the trick is, we know that if we want to integrate over a to b, c is any point within the interval, the integral from a to b can be written as integral from a to c and integral from c to b. So we are dividing the problem into sub problems by dividing the interval a b into sub intervals. Suppose we divide the interval into n sub intervals. So let us say, for our simplicity, we divide the interval into n equal sub intervals. That is not necessary, but for ease of convenience of application of the formula, we divide the interval into n equal sub intervals. So as shown in the figure, we get the points x0 is our a, x1, x2, x3, x4, xn equal to b, and all these points are equidistant, and the length of every sub interval is given by now b minus a by n, where n is the number of sub intervals, and our h is given by xi minus 1 when I runs from 1 to n. It is same as x1 minus x0 or x2 minus x1 or x3 minus x2, general xi plus 1 minus xi. And now we can write down our integral a to b fx dx as sum of the integrals of x0 to x1 fx dx plus x1 to x2 fx dx plus x2 to x3 fx dx, and so on continues up to xn minus 1 to xn fx dx. In other words, it is summation sigma of I equal to 0 to n minus 1 fx dx, integral xi minus 1 to xi fx dx. And now each of this integral we apply the trapezoidal rule to get the value. So our formula becomes a to b fx dx is equal to, the first formula x0 to x1 fx dx is h by 2 inside the bracket fx0 plus fx1. Second, x1 to x2 fx dx is h by 2 fx1 plus fx2. The third is h by 2 inside the formula fx2 plus fx3, and so on, last h by 2 fxn minus 1 plus fxn. So let us combine the sum. So we can say that approximately a to b fx dx is given by h by 2 fx0 plus summation of fxi I equal to 1 to n minus 1, and see all these terms except the last term have the coefficient 2 because they occur 2 times, once in the one term and as the first, once at the second term in the preceding term and as the first term in the next term. So the coefficient becomes 2 times sigma I equal to 1 to n minus 1 fxi and plus the last point at the point b, that is our xn point, f at the point xn. This form of the formula obtained by multiple application of the trapezoidal rule on each of the sub intervals and adding these form values is called composite form of trapezoidal rule. Let us review this composite form of trapezoidal rule. This h we can write as b minus a also. So this becomes b minus a into inside the bracket fx0 plus 2 times sigma I equal to 1 to n minus 1 fxi plus fxn divided by 2n. Sum of the coefficients in the numerator is 2n and denominator is also 2n. This looks like a weighted average of the function values at some chosen points of the points within the interval. Let us see what is happening graphically. You can have a look at the figures shown here. These figures one by one show that the number of intervals are increasing. In the first figure, sub interval is only 1. So trapezoidal rule is applied with our n equal to 1, and you can see the shaded figure and you can see how much is the error. Next figure, n is equal to 2, interval is divided into 2 sub intervals. Our abscissa are x0, x1 and x2. You can look, the strips are becoming smaller and the error, the shaded area shows that the error in the integration for the area under the curve has become smaller. Look at the next figure. in this case n is equal to 3, number of divisions have become 3 here, strips, the width of the strips has become further smaller, b minus a by 3 now this time, and so in this case again the discarded areas or the error in these areas has further reduced, and one more figure has been drawn when the number of subintervals has become 4, again the strips are getting further smaller and we can see that the error is reducing step by step. So, this very clearly shows that by applying trapezoidal rule in composite form we are able to reduce h, and that is why even theoretically and graphically the error in the trapezoidal rule will decrease. Now, the question is, see, when we apply the composite form, what would be the error term? What we derived was minus h cube by 12, second derivative at the point C, was the error term for application of the trapezoidal rule once. So, let us just derive the error formula for the composite form of trapezoidal rule. So, here again, as we know that integral of sum is the sum of the integrals, and so the error term in the composite form can be derived as a to b integral of fx dx is equal to sigma I equal to 0 to n integral xi minus 1 to xi I equal to 1 to n, and plus what we have is the error term. So, the error term will get sum. So, the combined error term for the composite form will be sigma I equal to 0 to n minus 1, f second derivative at the point xi I, and outside the summation sign will get minus h cube by 12. H is same for all the, because we have taken uniformly spaced points, they are equidistant points. So, h is same for each application of trapezoidal rule in the subinterval. So, result is minus h cube by 12 sigma I equal to 0 to n minus 1 f second derivative at the point xi I. Now, this EH here in the expression is h cube, the expression is h cube. Let us write this h cube as h square, and 1 h let us write as b minus a by capital N. So, we have minus sign as it is, b minus a h square by 12, and inside we have sigma I equal to 0 to n minus 1 second derivative at the point xi I by n, and that is the average of the second derivative values at some points. Already when we learned bisection method, we had talked about intermediate value theorem. The intermediate value theorem states that if the function is continuous on the interval a b, then it will take all the values between GA and GB. So, here again we apply this result. If the second derivative is continuous on the interval a b, then this term, which is the average of the values of second derivative at some points, would be attained at some point within the interval. Because this xi1, xi2, xin, they all are the points, these points xi0, xi1, xi2, xin minus 1, all these are the points within the interval. And so, the average a 1 by n sigma I equal to 0 to n minus 1 second derivative at the point xi I also lies between the least and the greatest values of second derivative of f on the interval a b. And so, we can say that there is some point xi which is not known to us, but we are sure it exists, such that second derivative of xi is equal to this. If I call this average as a, then this point is equal to a. And so, we can write down the error term as minus b minus a by 12 h square f second derivative at xi, where xi lies in the interval a to b. If we can find an upper bound on the second derivative of f on the interval a b, then we can say that we are sure that the error is less than or equal to b minus a by 12 h square m. And so, this error term is of the order of h square. Simple application, the error term was the order of h cube, but here the error is of the order of h square. And this suggests the smaller the h has to be less than 1, the smaller the h, less will be the error. So, if we are interested in computing the value of an integral correct to certain number of decimal places, we can calculate h from this error formula if we can find m, if we can find the bound on the second derivative of f on the interval, and we can compute how many subintervals are necessary to be able to apply the composite form. Let us just understand this by one simple example, one very well known example of error term. Suppose we are required to evaluate 0 to 1 e raised to minus x square dx correct to 4 decimal places. As our objective is to get the answer correct to 4 decimal places, our error term should be less than half into 10 raised to minus 4. So, we need to ensure to choose an h in such a way that we know that the error will not exceed half into 10 raised to minus 4. So, let us calculate what is the error term. Error term is minus b minus a by 12 h square second derivative xi. Here the integral is 0 to 1. So, a is 0, b is 1, fx is e raised to minus x square, b minus a is 1. So, to calculate m if possible, let us calculate the first derivative and second derivative of f. F dash x is minus 2x e raised to minus x square, and second derivative, further differentiate first derivative of f to get the second derivative. This gives minus 2 into e raised to minus x square minus 2x into minus 2x e raised to minus x square, and the expression becomes 4x square minus 2 e raised to minus x square. Now, e raised to minus x square is 1 upon e raised to x square, which is less than or equal to 1 on the interval 0 to 1, we know it, and so 4x square minus 2 is increasing function. It increases as x increases. So, the maximum value will occur at x equal to 1, and there the value of 4x square minus 2 is 4 minus 2, that is 2. And so, we are sure that the second derivative will not exceed 2 into 1, that is 2. So, we can say that error, if we are dividing the interval into n parts, so h is our 1 by n, then the error is less than or equal to 1 by 12 h square into m, which is 2. So, it is h square by 6. So, maximum error is less than or equal to h square by 6, which should be less than or equal to half into 10 raised to minus 4, which on calculation gives h square is less than or equal to 3 into 10 raised to minus 4. So, h is square root 3 into 10 raised to minus 2, that is 0.01732. And so, n is 1 by h, and that gives the value 1 upon 0.01732, approximately equal to 58. So, this implies that the number of subdivisions should be at least 59 or more safe to be 60 to ensure 4 place decimal accuracy. So, this is one of the ways to, if we can compute upper bound on the second derivative, then we can substitute in the formula and we can know beforehand that what h should be chosen. In other words, what should be the number of subdivisions to get the desired accuracy. So, let us look at the algorithm for it. What is our step? Our first, we have to input n, the number of subintervals which we need to calculate beforehand from the exact exercise. We will input endpoints a and b of the interval, and we will input fx, the given integrand. H will calculate from b minus a by n. We initialize our sum to be 0. Sum is nothing but the value of the integral, and then we calculate our abscissas x as a plus h into I for I equal to 1 to n minus 1. We have to do the procedure. X is x plus a into a plus h into I, and functions are to be computed at the point xi, and sum will be sum plus 2 into these fx. So, we can set the loop I equal to 1 to n minus 1, x is a plus h into I, and sum is sum plus 2 times f into x. These points I equal to 1 to n minus 1 are the interior points, and because there the coefficient of the function is 2 in the summation, and we complete this loop, and then our total final sum is sum plus value of function at the end points fa plus fb, and this sum we multiply by h by 2 at the last to get the value output of the integral. Programming code for the same is given in the e-text, so you can refer the e-text for the programming code for it. So here we got the answer 0 to 1 e raised to minus x squared dx as 0.74681, which is correct to 4 decimal places by taking 60 subdivisions. Similarly, we can consider another example 0 to 1 sin x by x dx needed to be evaluated correct up to 5 decimal places by applying composite trapezoidal rule. In this case, EH is less than or equal to half into 10 raised to minus 5. At 0, sin x by x as such is not defined, but limit x tends to 0, sin x by x is 1. So, integrand can be assumed to be 1 at the point 0. So, here again a is 0, b is 1, h is 1 by n, and similar exercise we do it. So, our EH is b minus a by 12 into h square into m. Now, in the case of sin x by x, m calculation is not that easy, but what can be done is we write down the Taylor series of sin x. We know that the Taylor series of sin x is x minus x cube by 3 factorial plus x raised to 5 by 5 factorial, so on. Divide by x, we get the Taylor series of sin x by x, and then we differentiate that Taylor series of sin x, because sin x by x will be 1 minus x square by 3 factorial plus x raised to 4 by 5 factorial and so on, and differentiate this, we get minus 2x by 3 factorial plus 4x cube by 5 factorial, so on, and again differentiate to get the second derivative minus 2x by 3 factorial plus 12x square by 5 factorial, so on, and this upper bound on interval 0 to 1 can be found, and that upper bound is 1 by 2. And so we can say the error is less than 1 by 24, 1 by n square, and that should be less than half into 10 raised to minus 5, and so it is h square is less than 12 into 10 raised to minus 5. So h you get in this case less than square root of 1.2 10 raised to minus 2, and so the number of divisions you get as 91.3. So number of subdivisions should be at least 93. So this is how, in the case when we can found m, we can calculate h beforehand. But there could be other examples where function integrand is not known. All we have is the value of function at discrete data points. In that case, nothing can be done. All what we can do is that whatever point the function values are available, apply the composite form of trapezoidal rule. A very famous example of it is the famous bags of pine bark mulch problem. I am just presenting a very simplified version of this problem here. It is about a plot of land at behind the bungalow, and that is to be covered with the mud with a particular amount of thickness. The bags of mud come of some sizes, and so it is found that the number of bags required is 1 by 12 from the calculation of the size of the bag and from the thickness of the layer of the mud required. The number of bags is 1 by 12 into area of the plot. The plot is very irregular, not of fixed shape. Its width is 6 feet, let us assume, but it is a very irregular shape as shown in the figure. So what is done is the height of the plot, means height we say is the width, its length of the plot is measured at the length of 1 feet, and these lengths come out to be 6, 7, 10, 11, 10, 8 and 5, let us say. And so now the integrals, area of the plot will be the integral 0 to 6. So 0 to 6 fx dx, we apply the composite form h by 2 outside, f0 plus 2 times f1 plus f2 plus f3 plus f4 plus f5 and plus f6. So it is h 1 by 2, we have measured our h is 1. So 1 by 2 inside the bracket 6 plus 5 plus 2 into 7 plus 10 plus 11 plus 10 plus 8, and that gives the answer 1 upon 2 into in the bracket 11 plus 2 into 46, that is 11 plus 92, it is 103 by 2, 51.5. As the number of bags are integers, we have to buy integer bags. So this is the area 51.5 and the number of bags is this integral value by 12. So we get 51.5 by 12, that is 4.3. Since we have to meet the requirement, the number of bags has to be larger than 4.3 and we can only buy integral number of bags. So the number of bags required would be 5. Now let us take the third case, and that third case is, though we know the integrand, but the integrand is so complex, computationally it is quite complex, and its derivative and second derivative becomes further complex. To compute their values and to compute the upper bound on the values on the interval may not be an easy task, or may not be feasible also many times. Under this case, how to proceed? See, we cannot know the estimate of the h beforehand before applying the formula. In this case, iterative process is applied. You divide the interval into certain fixed number of parts. You begin with journey from there and calculate the integral. Suppose I want the answer correct to 6 decimal places. I get the integral. Now we repeat the process each time by increasing the number of subintervals to twice as that in the previous case. So number of subintervals goes on becoming double of the previous case result, and your length of subinterval goes on becoming half of the previous case. And we calculate the integral values and compare the recent value obtained with the previous value, and if absolute value of this difference is less than the desired error, that means if the answer is correct, if two particular number of decimal places they become constant, they do not change, we can stop the process. So we can convert this application of trapezoidal rule to an iterative process, and will stop when we get the answer correct to desired accuracy. For it, see, this is one example whose result is already known. It is integrable, but for illustration purpose, let us take the example of velocity of a parachutist, which is given by gm by c 1 minus e raised to bracket c by m into t, where velocity is in meter per second. G is the gravitational constant given by 9.8 meter per second square. M is the mass of parachutist. In this example, let us take it to be 68.1 kg, and C is the dragging coefficient, which is given by 12.5 kg per second. We know the distance travelled by parachutist is going to given by 0 to t vt dt. So we need to integrate the velocity function. We can substitute these constants here and apply the trapezoidal rule. And in this case, we have not calculated the upper bound, and we are applying the iterative process. The iterative process is carried on, and let us say if we want the answer correct to 4 decimal places, we will stop the process when the two consecutive values differ by half into 10 raised to minus 4. So what you have is the table here, that this is calculated, and the table shows, see, we begin with 10 subdivisions. H was 1 because it was 0 to 10. We wanted to calculate the distance travelled by parachutist, let us say at t equal to 10. So n was 10, h is 1 in this case, and integral calculated came out to be 288.749146. The exact value of this integral up to 5 decimal places is 289.43515. Next, the number of divisions became double, so it became 20, h became half, 1 by 2, and the value of integral came out to be 289.263574. Next, the number of divisions still became double, so 40, h became 0.25, value of integral came out to be 289.392249. Again the n was doubled, 80, h became half of the previous case, 0.125, integral came out to be 289.424422. Next step, n was further doubled, 160, h was reduced 0.062500, integral value is 289.2465. Again double 320 because it is not becoming constant up to 4 decimal places. 320.031250, value is 289.434476. Then 640, h is 0.015625, value I is 289.434975. Next you again double, so 1280, h is 0.07813, value of integral is 289.435105. Next 2560, the h is 0.003906, value of the integral is 0.289.435136, and so on. At the end of 11 iterations, the value of integral becomes constant up to 5 decimal places, and the result is 0.43515. So this is how the process can be applied to get the integral correct to desired number of accuracies. The algorithm for this would be your input will be n, the initial number of subintervals, a and b as the endpoints, function as the given integrand, and epsilon the error tolerance to give the idea of how much accuracy is desired, and also to get m as the maximum number of iterations. Our sum initially will be 0, initialize the iterative process, the iteration counter k equal to 0, h we can calculate as b minus a by n, and old sum we can initialize the integral sum as old sum, I am calling it to be 0. And then for the loop, the same as the trapezoidal rule, the loop is there, I equal to 1 to n minus 1, we calculate the integral value x as a plus h into I, sum as sum plus 2 into fx, and we do it, and this sum when we calculate, sum is sum plus fa into fb, the same as we did in the previous example, and this sum we can print it and we will compare this sum with the old sum. If this sum with the old sum, the absolute value is less than epsilon, it would be half into 10 raised to minus p. If p is the desired decimal place accuracy, we will stop the process, otherwise we increase the counter k by 1 and again go back to step 3 and repeat the process of calculating the integral value. So this is how we can go on, and we also put upper limit by m as the maximum number of iterations to be performed, because it may happen sometimes that we may not be able to get the desired accuracy for the simple reason that the computation and round of errors may start more dominating over, because if we increase the number of intervals and big number of calculations are involved, the round of errors may start playing more important role and the desired accuracy may not be possible to achieve. In sum, what we have learned today is the composite form of trapezoidal rule, how it can be used to get the desired accurate results. It is a very good, convenient, very simple to apply, and it is used very commonly for solving scientific and engineering problems. But nevertheless, if the function computation is complex, the number of iterations needed to calculate the answer correct to desired place of accuracy becomes quite large. As you saw in the earlier example, it became more than 10,000 divisions of the intervals had to be performed, and so we look for a better case where we can work with less number of computation of the function values. So we would be learning the other formulas which are nothing but, because trapezoidal rule is obtained by taking n equal to 1, that is we approximated function by linear function. We will take further case, that is we will approximate function by second degree polynomial or third degree polynomial, and again derive the formula which are known as Simpson's 1/3 rule and Simpson's 3/8 rule, and see how they fare compared to trapezoidal rule. Thank you very much.